This is day 19 of the Advent of Cyber 2025. This challenge is called ISC Modbus Claus for Concern. Snow falls heavily over Werville as chaos erupts at TBFC headquarters. What should be the busiest shipping day of the season has turned into a disaster. Another chocolate egg? Shouts a frustrated warehouse worker, holding up yet another Easter-themed package. It's supposed to be shipping Christmas presents. The delivery drones buzz overhead, mechanical hums sounding almost mocking. Each one returns from its route empty, having successfully deployed its cargo, but the cargo's all wrong. According to the command center, where screens flicker with delivery statistics, everything looks normal on the surface. 1,000 presents in stock, 98% success rate, all systems are operational. But the phones won't stop ringing with confused citizens asking why they're receiving chocolate eggs instead of the toys and gifts they ordered. The logistics manager pulls up a delivery manifest. "Look at this," she says, pointing at the screen. "The system indicates that we delivered a teddy bear to the Miller family, but they received a chocolate bunny instead. The same weight, exact dimensions, but completely different items." Then, on one of the monitoring screens, a message flashes for just a second before disappearing. Exploit version 6.66, property of Hopsec Island. Why should Christmas have all the fun? King Malhare. Someone has compromised the drone fleet's control systems. The attack is sophisticated, falsifying sensor data, manipulating inventory selection, and erasing all traces. This isn't just a prank. It's calculated assault on Christmas itself. Your mission is clear. Investigate the TBFC drone delivery system. Cover how King Malhare's exploit team has compromised it. Restore Christmas deliveries before Sockmas is ruined. But be warned, King Malhare doesn't leave systems undefended. Traps are waiting for the careless investigator. One wrong move and you might make things much worse. A mysterious discovery. As you walk through the warehouse control room, something catches your eye. Crumpled piece of paper on the floor near the PLC terminal. Looks like someone dropped it in a hurry. You pick it up and unfold it. Handwriting is hurried, almost frantic. TBC drain control register map for maintenance use only. Holding registers, package type selection, Christmas eggs, chocolate eggs, Easter basket, and H1 delivery zone, 1 to 9 normal, 10 equals ocean dump, HR4, system signature version, default 100, current unknown, foils, boolean flags, C10 inventory verification, true equals system checks actual stock, false equals blind operation, protection override, true equals changes locked, monitored, normal operation for false, emergency dump protocol, true equals dump all inventory, false equals normal, audit logging, true all changes logged, false no logging, Christmas restored flag, auto set when system correct, self-destruct status, auto armed on breach, critical, never change HR0 while C11 equals true, will trigger countdown. Stare at the note, confusion washing over you. Register map, coils, what is all this? The terminology is foreign, HR0, C11, Modbus scribbled in the margin. Something about it feels important, like a key you don't yet know how to use. You pocket the note carefully, figure out what this means later, you think. For now, you need to understand the systems you're dealing with. Little do you know, the crumpled note will be exactly what saves Christmas. So, the learning objectives for this challenge are how SCADA, supervisory control and data acquisition systems monitor industrial processes, what PLCs, programmable logic controllers, do in automation, how the Modbus protocol enables communication between industrial devices, how to identify compromised system configurations in industrial systems, techniques for safely remediating compromised control systems, and understanding protection mechanisms and trap logic in ICS environments. So for this one, we need to start the virtual machine and the attack box. What is SCADA? SCADA systems are the command centers of industrial operations. They act as the bridge between human operators and the machines doing the work. Think of SCADA as the nervous system of a factory. It senses what's happening, processes that information, and sends commands to make things happen. TBFC uses the SCADA system to oversee its entire drone delivery operation. Without it, operators would have no way to monitor hundreds of drones, manage inventory, ensure packages reach the right destinations. It's the invisible orchestrator of Christmas logistics. So the components of the SCADA system are sensors and actuators. These are the eyes and hands of the system. Sensors measure real-world conditions such as temperature, pressure, position, and weight. Actuators perform physical actions. Motors turn, valves open, robotic arms move, and TBFC's warehouses, sensors detect when a package is placed on the conveyor belt, and actuators control the robotic arm that loads drones, PLCs or programmable logic controllers. These are the brains that execute automation logic. They read sensor data, make decisions based on programmed rules, and send commands to actuators. PLC might decide if the package weight matches a chocolate egg and the destination is Zone 5, load it onto Drone 7. We'll explore PLCs in detail in the next task. And there's the monitoring systems, visual interfaces like CCTVs, dashboards, and alarm panels where operators observe physical processes. TBFC's warehouse has security cameras on port 80 that show real-time footage of the packaging floor. These monitoring systems provide immediate visual feedback and literally watch what the automation is doing. And historians, databases that store operational data for later analysis. Every package loaded, every drone launched, every system change gets recorded. This historical data helps identify patterns, troubleshoot problems, and in incident response scenarios like ours, reconstruct what an attacker did. A SCADA in the drone delivery system. There's the package type selection. The system decides whether to load Christmas gifts, chocolate eggs, or Easter baskets onto each drone. This selection is controlled by a simple numeric value that determines which conveyor belt activates. Delivery zone routing. Each package must reach the correct neighborhood. Zones 1 to 9 represent different districts of Wervel, while Zone 10 is reserved for disposal. The ocean, a failsafe for damaged goods, but also a perfect target for sabotage. Visual monitoring. The CCTV camera feeds provide real-time observation of the warehouse floor. Operators can view which items are being loaded, verify system behavior, and identify anomalies. This visual layer is crucial during incident response. Inventory verification. While loading a package, the system can check whether the requested item actually exists in stock. When this verification is disabled, the system blindly follows commands, even if those commands are malicious. System protection mechanisms. Security features designed to prevent unauthorized changes. When enabled, these protections monitor for suspicious modifications and can trigger defense responses. Unfortunately, King Malheur has weaponized these very protections as part of its trap. Audit logging. Every configuration change, every operator login, every system modification should be recorded. Attackers often turn off logging to cover their tracks. That's precisely what happened here. Why SCADA systems are targeted. Industrial control systems, such as SCADA, have become increasingly attractive targets for cybercriminals and nation-state actors. Here's why. They often run legacy software with no vulnerabilities. Many SCADA systems were installed decades ago and never updated. Security patches that exist for modern software doesn't exist for these aging systems. Default credentials are commonly left unchanged. Administrators prioritize keeping systems running over changing passwords. For industrial environments, the mentality is often, if it works, don't touch it. A recipe for security disasters. They're designed for reliability, not security. Most SCADA systems were built before cybersecurity was a significant concern. They were intended for closed networks that were presumed safe. Authentication, encryption, and access controls were afterthoughts at best. They control physical processes. Unlike attacking a website or stealing data, compromising SCADA systems has real-world consequences. Attackers can cause blackouts, contaminate water supplies, or, in our case, sabotage Christmas deliveries. They're often connected to corporate networks. The myth of air-gapped industrial systems is largely fictional. Most SCADA systems connect to business networks for reporting, remote management, and data integration. This connectivity provides attackers with entry points. Protocols like Modbus lack authentication. Many industrial protocols were designed for trusted environments. Anyone who can reach the Modbus port 502 can read and write values without proving their identity. In early 2024, first ICS OT malware, Prostitute, was discovered. The malware can directly interface with industrial control systems via the Modbus TCP protocol, enabling arbitrary reads and writes to device registers over TCP port 502. King Malheur has weaponized these same tactics, not to cause blackouts, but to sabotage Christmas deliveries by directly manipulating the control system through the Modbus port. The next task will explore the PLC, the components he's actually compromised. So what port is commonly used for Modbus TCP? That is 502. That's correct. Programmable logic controller is an industrial computer designed to control machinery and processes in real-world environments. Unlike your laptop or smartphone, PLCs are purpose-built machines engineered for extreme reliability and harsh conditions. PLCs are designed to survive harsh environments. They operate flawlessly in extreme temperatures, constant vibration, dust, moisture, and electromagnetic interference. A PLC controlling warehouse robotics might endure freezing temperatures in winter storage areas, scorching heat near packaging machinery. They run continuously without failure. PLCs operate 24/7 for years, sometimes decades, without rebooting. Industrial facilities can't afford downtime for software updates or system restarts. When a PLC starts running, It's expected to keep running indefinitely. Execute control logic in real time. PLCs respond to sensor inputs within milliseconds. If a package reaches the end of a conveyor belt, the PLC must instantly activate the robotic arm to catch it. These timing requirements are critical for safety and efficiency. Interface directly with physical hardware. PLCs connect directly to sensors, measuring temperature, pressure, position, weight, and actuators, motors, valves, switches, robotic arms. They speak the electrical language of industrial machinery. Modbus is the communication protocol that industrial devices use to talk to each other. Created in 1979 by Modicon of Schneider Electric, it's one of the oldest and most widely deployed industrial protocols in the world. Its longevity isn't due to sophisticated features, quite the opposite. Modbus succeeded because it's simple, reliable, and works with almost any device. Think of Modbus as a basic request-response conversation. So you've got the client, PLC, what's the current value of register 0? Then the server, PLC, register 0 currently holds value 1. This simplicity makes Modbus easy to implement and debug, but it also means security was never a consideration. There's no authentication, no encryption, no authorization checking. Anyone who can reach the Modbus port can read or write any value. It's equivalent of leaving your house unlocked with a sign saying, "Come in, everything's accessible." So Modbus data types. There are coils, which have digital outputs where the values are 0, 1. An example use case is the motor running, is the valve open, is the alarm active. Have discrete inputs, which also have digital inputs of on and off, value of 0 or 1, and you'd use that for if the button's pressed, door closed, sensor triggered. There are holding registers, which are analog outputs of values 0 to 65535. They hold, and they're used for temperature set point, motor speed, zone selection. Then input registers, which are analog inputs, which hold the current temperature, pressure reading, and flow rate. The distinction between inputs and outputs is important. Coils and holding registers are writable and change their values to control the system. Discrete inputs and input registers are read-only. They reflect sensor measurements that you observe but cannot directly modify. In TVFC's drone control system, you'll find holding registers storing configuration values. So there's the package type selection, the delivery zone, and system signature. There are coils for inventory verification, protection mechanism, emergency dump protocol, audit logging, Christmas restoration status flag, and self-destruct mechanism. And Modbus addressing. Each data point in Modbus has a unique address. Think of it like a house number on a street. When you want to read or write a specific value, you reference it by its number. The critical detail is that Modbus addresses start at 0, not 1. This 0 indexing catches many beginners off guard. When documentation mentions register 0, literally means the first register, not the second. So for this one, holding register 0, the first one is the package type selector, and so on. So Modbus TCP versus serial Modbus. Originally, Modbus operated over serial connections using RS-232 or RS-485 cables. Devices were physically connected in a network. This physical isolation provided a degree of security. Needed physical access to the wiring to intercept or inject commands. Modern industrial systems uses Modbus TCP, which encapsulates the Modbus protocol inside standard TCP/IP network packets. Modbus TCP servers listen on port 502 by default. This network connectivity brings enormous benefits: remote monitoring, easier integration with business systems, and centralized management. It also exposes these historically isolated systems to network-based attacks. King malware exploited exactly this vulnerability. The TBFC drone control systems, Modbus TCP port 502 was accessible over the network without any authentication required. He didn't need to break into the facility or tamper with wiring. He simply connected to port 502 and started issuing commands as if he was authorized. Security problem. Modbus has no built-in security mechanisms. No authentication. The protocol doesn't verify who's making requests. Any client can connect and issue commands. No encryption. All communication happens in plaintext. Anyone monitoring network traffic can see exactly what values are being read or written. No authorization. There's no concept of permissions. If you can connect, you can read and write anything. No integrity checking. Beyond basic checksums for transmission errors, no cryptographic verification that commands haven't been tampered with. Modern security solutions exist: VPNs, firewalls, Modbus security gateways, but they're add-ons, not part of the protocol itself. Many industrial facilities haven't implemented these protections, either due to cost concerns, compatibility issues with legacy equipment, or a lack of awareness. So connecting the dots. Now you understand why the OpenPLC web interface showed nothing useful. King Malware bypassed it entirely, connected directly to the Modbus TCP port, and manipulated the registers and coils that control system behavior. The note found the maintenance technician must have discovered what was happening and started documenting the compromised values. The warning at the bottom, never change HR0 while C11 true, suggests they figured out the trap mechanism before getting interrupted. In the next task, we'll use Python and the PyModbus library to investigate the systems exactly the way King Malware attacked it, by directly reading and writing Modbus values. Time to see what he actually changed. So now that you understand the basic concepts related to ICS and Modbus, we will analyze the compromised TVFC drone control system and learn how to safely restore it. So for initial reconnaissance, as with any incident response scenario, we begin with reconnaissance. Let's discover what services are running on the target system. So in our attack box, we will bring up a terminal and we will then use nmap to scan the virtual machine. So nmap-sv, and we'll search on ports 2280. 502 and our virtual machine IP address, and we will run nmap. Okay, it finished running, and we can see port 22 is open with SSH, port 80 is open with HTTP, and port 502 is open and saying MBAP. So it appears to not be 100% sure what's running, although in there's one, it's saying Modbus. So we'll continue on. So the key findings are port 80 HTTP service, port 502 Modbus TCP. So if we now open up Firefox and then in the browser navigate to the IP address of the virtual machine, a web page should come up because it's running on port 80. So in the browser go http:// then the IP address of the virtual machine. We can see it here. That is compromised, disarmed. So through the security camera, you can see the warehouse floor in real time. Robotic arms are busy at work and the conveyor belts are running smoothly. Something is wrong. Instead of Christmas presents, you see pastel-colored chocolate eggs being sorted, Easter-themed packaging on the assembly line, and delivery drones are loading Easter eggs instead of gifts. Status displayed in the corner shows compromised. The visual confirmation tells you the problem is real and active. The system isn't broken, it's working perfectly, just delivering the wrong items. This is a classic sign of logic manipulation rather than a system failure. Now for Modbus reconnaissance. So we will need to return back to our terminal and using pip3, going to install the Python package PyModbus and specifically version 3.6.8. I should have probably read what it said. It says on the attack box it's already pre-installed. So let's cancel that and go into Python 3 to bring up the Python shell and let's write out what they have. So from PyModbus.client import Modbus TCP client and do client is equal to Modbus TCP client and connect to the virtual machine, enter the IP address and then port equal to 502. Now if client dot connect, you will then print connected and we'll do else print failed. Let's see if it worked and it has connected. So now I'm just going to copy and paste the values in to make it easier. So let's paste in the result. So if it's not an error, you're then getting the package type from the registers. You're then going to print out what the package type is. And based on what the package type is, we'll see what is there. So let's see. So currently package type 1 chocolate eggs. Next we'll look at the delivery zone. Currently delivery zone 5, normal delivery zone. And since we're basically just copying what they're doing, we'll just look at the code here. So system signature 666 exploit detected. Inventory verification is false, which is disabled. System not checking stock. Detection overrides true. So changes are being monitored. And self-destruct armed is false. Not armed yet, so it's safe. So we are now going to be creating a new script and we'll do nano reconnaissance.py and we're going to copy everything from this and put it inside this file. So let's take a look at what the script is doing. So it's using the Modbus, connecting to the virtual machine on the IP and port, making sure we're connecting, and we're going through the registers and verifying what values they have, going through the calls, verifying the values and printing out that. Okay, so to save this file, Control X, Y, then enter, and then using Python 3 we run reconnaissance.py and this will produce the report for us. You can see all the current values within it. So based on our reconnaissance, we need to disable protection mechanism and change package type to Christmas gifts, enable inventory verification, enable audit logging, and verify C15 never got armed. So we're now going to be creating nano restore Christmas.py and we'll be copying this script. So Control X, Y, enter, save it. Now Python 3 restore Christmas and Apparently after doing that, if we go back to the web browser and we refresh the page, oh, my mistake, I apparently didn't copy this properly and add it to the file because it's saying reconnaissance report. So I'm going to go back in nano restore Christmas. It might be easy just to remove the restore Christmas and then create a new one. We paste that in. This looks to be correct now. So now if we run it, okay, that appears to be actually changing it. Well, first things first, we can see we've got the flag here, which we will copy and paste down here. And now if we go back to here, we can see system restored. Okay, well, that is day 19 of Advent of Cyber 2025 complete. If you like this video, make sure to like and subscribe.